Today we have with us Turnbull. Dr. Turnbull received his PhD from Princeton in 2013 with a thesis on Raman amplification. He then joined Lawrence Livermore for 3 years, where he helped maintain the NIF backscatter diagnostics and executed a variety of experiments ranging from ICF implosions to plasma photonics on NIF as well as the Jupiter Laser Facility. In 2016, he joined the University of Rochester's Laboratory for Laser Energetics, where he continues to focus on experimental laser plasma interactions related to ICF. Last year, he received the Excellence in Fusion Engineering Award for the Fusion Power Associates, and he recently became Laser Plasma Interactions Group Leader at LLE. And so in today's talk, I'm very much looking forward to it. And also, please, if you have any questions, please enter them into the chat field and I will read them at the end. Also, please turn off your videos. It helps with bandwidth. Sometimes I think like last week's was running a little too slowly. And it's good to save on our bandwidth. And also, please be aware that this talk is being recorded. So if you're not comfortable with that, please log off. And also be aware that it is an unclassified meeting with external people logged in. And thank you very much for coming, and please enjoy the talk. Please take it away, David.
All right, thanks for that intro, Paul. Thank you all for coming, although I haven't been able to see who's logged in since I started screen sharing. The title of my talk is Non-Maxwellian distribution functions and their impacts on cross-beam energy transfer and absorption. The plot I'm showing here on my title slide is a plot of cross-beam energy transfer gain or NIF Holrom conditions. And it's the case that you would expect for a non-Maxwellian electron distribution function driven by laser heating, normalized by the conventional result for a Maxwellian assumption. And what it shows is that the laser heated distribution functions are expected to reduce cross-beam energy transfer by about 30% over NIF's tuning range. To that a little bit later in the talk. So in summary, non-Maxwellian distribution functions impact a variety of processes in ICF environments, including cross-beam energy transfer and absorption. It's a bit of a survey talk. I'm going to go through 5 results that are kind of now spread out over the past 5 years or so. I'll first show some 2-beam pump probe experiments that we did at the Jupiter Laser Facility, which observed good agreement with traditional linear kinetic CVET modeling at plasma wave amplitudes beyond their regime of ICF relevance. And that started to call the usual saturation clamp that's been imposed previously in codes into question. However, multi-beam experiments at LLE with more ICF relevant conditions have now shown non-Maxwellian electron distribution functions driven by laser heating can strongly impact CVET, and extrapolating to NIF gives 30% less gain. That's the plot I showed on my title slide. We think a non-Maxwellian inline CVET model should improve the predictive capability of integrated implosions, and that's under development by the LPI group there. I'll then branch out from CVET a little bit, and I'll mention that other processes are sensitive to the tails of the electron distribution function, for example, Raman scattering. And these tails were measured with angularly resolved Thomson scattering, a new instrument at LLE, and found not to conform to any single theory yet derived. I'll also mention some recent measurements testing the effect of non-Maxwellian EDFs on absorption, a very recent result that has sparked some interest both here and there at Livermore. And finally, I'll go back to CVET and I'll mention that crossbeam is also sensitive to the ion distribution function, but energy transfer modifies the ion distribution function in a way that can feed back on the CVET itself. It's a little bit of a survey talk, but there are 2 themes that I hope you'll see run through the talk. One is cross-beam energy transfer that I'll touch on several times, and the other is non-Maxwellian distribution functions, which I'll touch on several times. I'm going to talk about work that's been a large collaboration with many people here at LLE, there at Lawrence Livermore, as well as at other institutions like CNRS, Alberta, and Los Alamos. and it's an honor to present all of their contributions. So since crossbeam is one of the themes running through the talk, I wanted to, and this is an audience that probably has a very wide variety of backgrounds, I wanted to give a brief background to crossbeam. So crossbeam energy transfer is seeded stimulated Brillouin scattering, the decay of an incident photon into a scattered photon and an ionized wave phonon. So if you interact two lasers in plasma and their frequency shifted such that they can satisfy the frequency and wave number matching conditions, which essentially just convey conservation of energy and conservation of momentum, you can have energy transfer from the higher frequency beam to the lower frequency beam. And at NIF, of course, we often think of using wavelength detuning to satisfy these matching conditions. But flows enable coupling between frequency degenerate lasers, and that makes CBET very difficult to avoid in ICF environments. So instead of a stationary plasma, now imagine this plasma is flowing to the left. In that moving frame, the laser from the left appears Doppler upshifted, and the laser from the right Doppler downshifted. And so you can still satisfy the frequency and wave number matching conditions without any frequency difference in the lab frame. And since flows are ubiquitous, this makes crossbeam fairly ubiquitous in ICF experiments. So crossbeam is an important effect in both indirect and direct drive ICF. In indirect drive, CBET was primarily controlled by wavelength detuning, at least historically, but it's important to keep in mind that flow is also important, and setting delta lambda, as it's called there, equal to 0 does not ensure that there's zero energy transfer or even zero net energy transfer, and historically it was found not to be the point of minimum energy transfer. In direct drive, CBET is primarily controlled by the flow velocity in the coronal plasma surrounding the driven target, but their wavelength detuning is proposed as a mitigation strategy, and that's been recently demonstrated on NIF. So in both cases, an improved understanding of CBET will impact the design of the integrated implosions. Early experiments of observed CBET but proved difficult to calculate accurately. So again, I said I haven't seen who's called in, but I've seen Bob Kirkwood called in on an earlier one of these talks, and he did a lot of the seminal experiments on this between 20 and 25 years ago, going back to gas bag experiments on NOVA, as well as exploding foil experiments. And in both cases, energy transfer was observed, but quantitative agreement was lacking. So these experiments provided proof of principle, but not quantitative agreement. What about in integrated experiments? Well, the inclusion of a CBET model has been instrumental in simulating recent direct drive implosions, but ad hoc multipliers are still typically required. So I'm showing here the recent NIF results where the introduction of wavelength detuning was shown to affect the morphology of an implosion, and importantly, in a somewhat predictable way in simulations. However, typically a multiplier on the CBET model is still required to reproduce things like implosion trajectories, and the persistence of such multipliers limits confidence in our ability to simulate CBET. Similarly, CBET was integral to the success of early NIF indirect drive experiments, but ad hoc clamps were later added to account for apparent saturation. So Siegfried gave a talk in this series several weeks ago, and I'm showing one of the iconic results from his science paper that I'm sure many of you are co-authors on, showing the ability for wavelength detuning to be used to control implosion symmetry in early NIF hull rumps. However, it soon became apparent that the amount of energy transfer based on integrated observables like shape was less than what was expected from linear kinetic theory. And so a clamp was implemented in the code as later detailed by Pierre Michel and others in order to effectively limit the amount of energy transfer. The difficulty in calculating CBET reliably has been one was one factor that pushed the indirect drive program away from high gas forums, and we think demonstrating improved understanding could restore a larger operable design space. So that kind of lays the foundation for why we've been doing these focused CBET experiments over the past few years. And we first developed a CBET platform at Livermore's Jupiter Laser facility to test and improve models. We developed a very simple two-beam pump probe platform where we would use a supersonic gas jet nozzle to provide a medium in which to conduct the experiment. We would ionize that gas jet with a high energy pump beam, diagnose the plasma conditions with both interferometry as well as Thomson scattering, and then diagnose the probe beam subsequent to interacting with the pump beam in the plasma. And the idea was that by wavelength detuning and uniform, well-characterized plasma, we could isolate cross-beam physics from hydrodynamic uncertainty. What we found is that the observed CBET was in reasonably good agreement with the linear kinetic theory used in indirect drive calculations for small ion acoustic wave amplitudes. So I'm plotting on the left the experimental data, which is CBET gain or amplification as a function of wavelength detuning between the probe beam and the pump beam. And that's overplotted with the linear kinetic theory that's used to model indirect drive holograms. And when the incident probe intensity was very low, we see very good agreement with the linear theory. Now there are a couple caveats here, and the biggest one is that I had to tweak the ion composition in order to match this resonance peak location from what I would have expected. So there are still some questions, but in general, this represented at the time a significant improvement in quantitative agreement. However, we did find that increasing the incident probe energy led to deviation from linear theory. So now I'm showing what happens when we start with a more intense probe. And what happens then is we're driving larger plasma waves, and there's a larger amount of energy transfer from the pump to the probe for the same gain. And there, even though the linear kinetic theory would predict the same gain, we see deviation from the theory. However, we did find that vampire simulations by Arno Collitis could reproduce a large amount of data fairly well with a single clamp at the delta n on n, or ion acoustic wave amplitude, of 1.5% level. And that's shown here, where the model is doing a fairly good job of reproducing the peak reduction for every data set. Note that Arno did use the nominal methane composition, so the nominal ion composition we expected, and that reveals this anomalous peak shift that's still not very well understood. One of the takeaways at the time, though, was that this amplitude, this parent saturation threshold of 1.5%, was higher than the FLAM typically invoked in ICF holograms. And that suggests that clamps at lower levels should not be expected. We've since gained more insight into what's probably happening here, and if I have time for the last section of my talk, I'll circle back to this. So despite what I would have argued was the best CBET validation to date, we still had questions that remained. So there was this anomalous peak location, and that was similar to what Bob Kirkwood observed on NOVA. We lacked certain key measurements, for example, ion temperature. Arguably, the conditions were all far from ICF relevant. We had a limited number of beams and geometries, and multi-beam physics is, of course, particularly important for ICF. And we also had a limited ability to understand the saturation that we observed. So clearly, there was motivation for additional experiments. And that brings me to the work that we've been doing at LLE with the new Top9 platform. So the tunable omega P9 beam, or Top9, which is wavelength tunable over more than 3 nanometers in the UV, was built at LLE to continue CBET studies and develop understanding that can be scaled to ignition plasmas. I'll note that this was something that was pitched at the LPI workshop back in 2016 and it got a lot of support from the community. And we went forward and developed this capability within about a year and a half from that point. And we've been doing experiments for about 2 years now. So this beam was built, yes. So it's an Omega EP beam with a new wavelength tunable front end and a new transport system that relays that beam to the Omega target chamber for joint operations. We bring that beam into the P9 port. We typically use our gas jet system to provide the medium. We typically diagnose it with Thomson scattering, and we also have a transmit beam diagnostic. So you can see it's very much modeled after the platform that we developed at Jupiter. And the initial experiments that we performed with Top9 studied the effect of non-Maxwellian, specifically super Gaussian electron distribution functions driven by inverse Bremsstrahlung heat. So this is a very old idea dating back to Bruce Langdon's seminal 1980 paper, in which he showed that inverse Bremsstrahlung absorption preferentially heats low energy electrons, distorting the EDF away from a Maxwellian. He defined the parameter alpha, which has come to be referred to as the Langdon parameter, which is just the ratio of the inverse Bremsstrahlung heating rate to the electron-electron collision rate, which acts to restore a Maxwellian distribution. So in the limit of alpha much less than 1, you expect to retain a Maxwellian. For alpha much greater than 1, he showed you would trend towards a super Gaussian of order n equals 5. And later, Jean-Pierre Mott showed with Fokker-Planck simulations that moderate heating in between these two limits produces intermediate super Gaussian EDFs, and importantly, that they can be predicted by this convenient formula shown here, which is just a function of the Langdon parameter alpha. Despite potentially impacting many different processes in ICF plasmas, experimental evidence for such distribution functions has been scarce. And so the laser-heated distribution functions are, we suspect, not often considered in situations where they may be relevant. Super Gaussian EDFs also impact the ion acoustic waves that mediate cross-beam energy transfer. And this goes back to another seminal paper by Bedros-Afan in 1998, who showed that the smaller number of low-energy electrons available to shield ion oscillations increases the effective frequency of ion acoustic waves. He provided this modified dispersion relation. This is the traditional simplified Maxwellian dispersion relation modified by this square root term here, which has gamma functions in it, but is only a function of the super Gaussian exponent m. And if you plot that term on the right, it shows that this effect increases the frequency of ion acoustic waves between 0 and 20% as a function of the super Gaussian exponent. And Bedros conjectured at that time that this might explain resonance peak anomalies that were seen in the early experiments, such as Bob Kirkwood's experiments. So the experiments were executed as shown. We brought the Top9 beam into our gas jet plasma. We interacted that beam resonantly with one nearly co-propagating pump. But we could add nearly counter-propagating beams, and by virtue of their geometry, they didn't transfer energy with these beams. However, they could modify the isotropic electron distribution function in which the energy transfer is taking place. And then, of course, we diagnosed the probe beam with the transmitted beam diagnostic. And an example of the data is shown here, which shows the amplification during the time period when the pump beam was on, and then decaying back to the level of the incident probe beam when the pump beam is turned off. And what we found in these gas jet plasmas is that Thomson scattering clearly shows the need for a non-Maxwellian electron distribution function, and a Maxwellian assumption would give order tens of % errors in electron density, electron temperature, and ion temperature. So I'm going to walk you through one of the fits to try to convince you of that. So we're focused on this latter time period here, where the plasma preforming beams, of which there are many, have already turned off. And we're focused on this time when there are only a few beams on, and we can calculate all of their Thomson scattering features. And I'm showing here a fit to both the electron plasma wave feature and the ion acoustic wave feature, and it's essentially a perfect fit, and it requires an electron distribution function that's super Gaussian of order m equals 2.75. And to convince you that you need the super Gaussian distribution, I'm showing what you get if you make the usual Maxwellian assumption, and if you keep the plasma parameters that you infer from the super Gaussian fit, you see that you fit neither the electron features nor the ion features. If you relax the electron feature fit and focus on the ion feature fit, you can actually obtain an equally good fit to your non-Maxwellian fit. However, it's about 20% higher temperature, and moreover, the electron feature discrepancy is telling you that there's an issue with the distribution function. And conversely, you can try to focus on improving the electron feature data, but it's actually not really possible to match that data. And further, you compromise your ion feature fit as well. So the broad point here is that, the super Gaussian assumption does a much better job of matching both the electron and ion features. And I'll just note a couple other things. One is the degeneracy here in the ion features. That was actually noted theoretically back in 1997, and that does have implications for early Thomson scattering experiments that only had ion feature data. They could have been naive to this issue. And the other thing I'll just point out are these errors here. If you have a Maxwellian assumption and no knowledge of your distribution function, or you're invoking the usual Maxwellian assumption, you can get tens of % errors. And that's delved into in more detail in Avi Milder's POP from 2019. And intensity scaling showed a clear increase in the super Gaussian exponent of the non-Maxwellian EDF with existing theory. So in that same platform with only heater beams, we increased the number of beams from 1 to 2 to 3 to 4. They all have the same smoothing and nominally the same intensity. So that increased the temperature, but also the Langdon parameter scaled with the intensity. If you plug that Langdon parameter into the formula in Jean-Pierre Mott's paper, you get a predicted super Gaussian exponent shown in the bottom row here. And that is in very good agreement with the measured super Gaussian exponent from the Thomson scattering data shown here in the 4th row. And so that confirms that the formula can be used in simulations to convert intensity along with temperature directly to distribution function. Of course, it wasn't a Thomson scattering experiment that we were doing. It was a cross-beam energy transfer experiment. And the CVET data also confirmed the impact of the non-Maxwellian electrons on ion acoustic waves that was evident in the Thomson scattering data. So I'm showing here the cross-beam energy transfer gain for the case where we have additional counter-propagating heater beams exaggerating the non-Maxwellian distribution function. And we see that you really need to account for the measured super Gaussian distribution in order to match the measured cross-beam gain. In the case of a single pump only without those additional counter-propagating heaters, the two models are much closer to one another, and it's harder for the data to discriminate between the two. And that probably makes it easier to understand the Jupiter results, which were also a 2-beam experiment, and why we didn't need to invoke these super Gaussian distributions. The impact of the super Gaussian EDF on ion acoustic waves is primarily a resonance shift concern in strongly damped plasmas. So I'm showing an idealized single cross-beam energy transfer gain where you're just modifying the super Gaussian exponent from m equals 2 or Maxwellian to 3 to 5. Note that the peak gain does not change much, nor does the integral under these curves, and that's more clearly shown in this plot on the right. However, if you are doing an experiment where you're using wavelength detuning and you're placing your probe at a certain wavelength and looking at the local change in energy transfer, then you can see here in this plot on the lower left that you can have a very big discrepancy from linear theory if you're naive to the distribution function. And so that means this most strongly affects situations where seabed doesn't integrate over a flow gradient, and that makes it more indirect drive relevant rather than direct drive relevant. But it does also modify the detuning requirements for seabed mitigation in direct drive. And that gets me back to the plot I showed on the title slide, which is a calculation for typical NIF conditions suggests that non-Maxwellian EDFs lowers seabed gain by tens of % over the relevant tuning range. So for a NIF LEH, how do the conditions vary compared to our top 9 plasma? Well, Z is lower, being pure helium, and the temperature is much higher, and both of those reduce the Langmuir parameter. However, overlapped intensity in the region where you have all 96 beams overlapping can be much, much higher, and that more than compensates. That gives a predicted supergaussian exponent, which is on the order of 3, not far from where we were in the top 9 experiments. And if you compute the expected quad by quad energy transfer for an average inner beam compared quad from each average outer quad as a function of wavelength detuning, it's about a 30% reduction on average that you expect for the non-Maxwellian model compared to the Maxwellian model. Of course, it's somewhat spiky because you're summing over many discrete resonances, and different beams will come into resonance at different times. But on average, over NIF's tuning range, it should be a systematic reduction in crossbeam. And that's consistent with the direction of reducing energy transfer that's typically imposed by the clamp. So we think that implementing the non-Maxwellian model will improve the prediction of seabed space and time dependence in indirect drive, and it will reduce and may eliminate the need for a saturation clamp. And again, this is an ongoing project with the LPI group at Livermore. So I'm going to deviate from crossbeam for several topics. So seabed, of course, is determined by bulk electrons, being electrons with velocity near 0 or near the peak of the distribution function. But many processes are sensitive to the tails of the electron distribution function. Subsequent simulation work consistently validated Mott's formula for bulk electrons, meaning electrons between about 0 and 3 V thermal. But some have argued that the tails of the distribution function are likely more Maxwellian than the pure super-Gaussian distribution for various reasons. And processes that could be affected by the tails include X-ray emission, electron plasmoid instability growth rates, heat transport, etc. So the ability to measure the electron distribution function without assuming its functional form would be extremely useful. Thompson scattering with additional collection angles could help to fill in the electron distribution function. So if you think about what we typically are doing with Thompson scattering, we have a fixed incident probe beam that sets this incident wave number. We have a fixed collection optics, which sets the scattered wave number. And together, those two vectors define the plasma wave number that's being probed. And given that wave number, you're probing a certain phase velocity for your plasma wave. And if that wave is an ion acoustic feature, then you're probing near 0 with respect to the electron distribution function. And then you're making an assumption as to its functional form to extrapolate the rest of the distribution function. And usually that assumption is Maxwell. If you're measuring an electron feature, it's similar, except that you're measuring a point out and then closer to the tail of the distribution function. And then again, extrapolating the rest of the distribution function with an assumption. What we showed here is that we measured both ion features and electron features showed that the Maxwellian assumption was not consistent with those two measurements. However, if you replace that assumption with a super Gaussian assumption, you could reconcile the two measurements. But that doesn't necessarily mean that you've constrained the distribution function everywhere. And in particular, you could have hotter fields that weren't measured with our Thompson scattering system. You could think about doing it a different way. If you added a second collection optic, then you're probing a slightly different plasma wave number, and therefore a different point on the distribution function for your electron plasma wave features. And you could continue to build up the distribution function in this way by adding more collection angles. So the angularly resolved Thompson scattering instrument allows for continuous collection over 120 degrees in scattering angle. This is a PhD project of Avi Milder under Justin Frola. Avi is finishing up just within the next month or so, and actually you may hopefully saw his talk recently when he was applying for the Lawrence Fellowship. So this is an instrument that collects a scattered light over a very wide solid angle here, and then has a kind of tour de force imaging system that relays that to a two-dimensional detector. And what you get is a 2D image where one axis is now scattering angle, which is effectively different phase velocities that you're probing on the distribution function. And what Avi does is he just makes an arbitrary distribution function and does a forward fitting method in order to obtain the best fit to the data. And what he found, an example of what he found is shown here on the right in the black points. And all I will say about this is that the tails of the EDF were observed to deviate from the bulk super Gaussian, as many have predicted. But as yet, the shape of the tail is not well matched by any single theory. And so that does have implications for many of the processes I mentioned earlier. In general, this promises to be a very powerful diagnostic for the measurement of arbitrary electron distribution functions. So I'll mention another recent project, which is measuring absorption. So the key result in Langdon's seminal paper actually pertained to absorption, and that's specifically a widely used reduction factor. So Langdon concluded that the impact of the lower number of electrons near f of b equals 0 in the laser heated distributions reduces the absorption by this factor shown here, which is just a function of alpha. And essentially, the physics is very similar to the impact on CBET in that you're sensitive to just the f of b near 0. This factor is widely used in rad hydrocodes to modify the inverse Bremsstrahlung absorption coefficient, but to our knowledge, this conclusion has remained largely untested over the past 40 years. So additional experiments at LLE, and I'll note that they were just 3 months ago, so we're very much still in the kind of weeds trying to understand the measurements. But they've aimed to measure absorption while spatially resolving plasma conditions along the entire probe path. So the requirements were to measure density, electron temperature, and ion temperature along the entire probe path through the plasma. Absorption, of course, is a path integrated measurement. We can only we're really measuring transmission, after the fact, and so we need really the plasma conditions to be well constrained along the entire path. We wanted to measure absorption with plus or minus 0.1% accuracy. We think we achieved plus or minus 0.2% accuracy. And there's a whole host of competing instabilities that we had to avoid in order to really optimize the absorption measurement and prevent artifacts. We think we did a pretty good job of doing that. So the way we did this was we had a large number of omega beams that were preforming this plasma. And after a short 0.3 nanosecond delay, we sent in the short 100 picosecond Thomson probe beam at 2 omega. Through the center of the plasma that was formed. We measured transmission with a combination of a wedge pickoff upstream and a transmitted beam diagnostic downstream. And then we do Thomson scattering in imaging mode, which allows us to spatially resolve the conditions along the probe path. Nearly the entire probe path through the plasma was captured within the imaging Thomson scattering field of view, and that provides a tight constraint on absorption. So shown here is one example of a shot where we measured density, temperature, and superconduction exponent. And the main point here is that the density nearly drops to zero in the Thomson field of view. With approximately constant density, heater beam energies were varied to access different temperatures and superconduction exponents, hence also the Langdon factor. And so we actually got 4 shots on the day, which actually takes 8 shots because each had a only background shot. And we scaled the omega beam energies to increase the temperature and the superconduction exponent. And then you can compute using the measured plasma conditions the expected path integrated absorption. So that's taking into account the density, the electron temperature, and effectively superconduction exponent up through the Langdon factor. And that's using the standard theory of inverse Bremsstrahlung. And I'll just point out that log lambda is coming from the NRL formulary radiation section. Again, making the point that the absorbing region was almost entirely contained within the Thomson field of view. And you can see that here where there's an inflection point within the Thomson field of view where absorption in the wings here is going to zero. And that means any unmeasured absorption outside the field of view should be negligible. And of course, we measured absorption. So we did that by, again, having a takeoff upstream to a CCD camera and then the transmitted beam diagnostic downstream. And we did 2 shots on the day where we just fired the beam through vacuum in order to calibrate the system. And then we could use that calibration on data shots to infer the absorption. And one key point here is that our transmitted beam diagnostic has greater than full aperture collection. And we could tell that the beam spray was minimal and the signal was going to zero within the field of view of the collection. And that rules out artifacts such as beam spray and filamentation. I'm not going to go too deeply into the results. All I will say here is that measured absorption is about 50% higher than what we would expect from the conventional theory at all heating levels. There's a lot that we're digging into to try to reconcile this discrepancy. Mark Sherlock is really driving those efforts at Livermore. Many explanations have been considered. You could worry about backscatter filamentation, whether the Langdon factor is correct. There are other potential sources of absorption that you might worry about, such as speckle to ion heating, stochastic speckle heating. I will say now that we actually conducted these experiments in order to look for this new effect that Mark Sherlock has proposed, where the speckles enhance absorption over what you would expect from inverse Bremsstrahlung. We now think that based on the parameters on the shot day, we didn't quite access this regime. And so we don't think this mechanism explains this discrepancy. Mark and Pierre have been digging into the Coulomb logarithm, and that's clearly a big multiplier on absorption calculations. And so I look forward to hearing more what they're finding. So I'll just say that analysis is ongoing, and we expect this campaign to be continued next year. The point for me is just that absorption is really the most fundamental process in so many of our experiments, and we should probably be sure we're getting it right. I think I have time, so I'm going to deviate from electron distribution functions and move on to ion distribution functions. But I'm getting back to CBET, actually. So Aaron Hansen has recently observed cross-beam energy transfer saturation using the top 9 LPI platform with implications for indirect and direct drive ICF. The way that he conducted the experiments is shown here. He brought in the top 9 beam. He interacted that beam with up to 4 pump beams. he began at low intensity, low incident probe intensity, where recall plasma waves are small, and we expect linear theory to be more valid. And indeed, he found that if you measure the gain as a function of wavelength detuning, it's in quite good agreement with the linear kinetic theory. And then again, in the same vein, or in the same spirit of the JLF experiments, he increased the probe intensity to drive larger plasma waves, involve a larger amount of energy transfer. And here too, he starts to see discrepancy from the linear kinetic theory. So in the case of the lowest intensity probe, shown here, time-dependent gain, which drops a little bit as a function of time, but it's quite consistent with what you would expect from just the change in plasma density. But as he increased the top 9 intensity, what he sees is this more rapid reduction with a characteristic shape where it drops steeply about 200 picoseconds and then plateaus at a lower level. And again, this is making the results inconsistent with linear theory. One advantage that Aaron had over our earlier Jupiter experiments is Thomson scattering ion acoustic wave features, which indicated significant ion heating during the CVET interaction. So we only had electron feature Thomson scattering at Jupiter, and here the addition of ion feature Thomson reveals that in the case of small ion acoustic waves where there is a small amount of energy transfer, the ion temperature stayed low, where typically in our gas jet plasmas, it's usually around 20% of the electron temperature because the colibration is slow, and there's nothing really coupling energy directly to the ions. However, in the case of of a saturated shot, where there was a large amount of energy transfer, he saw a very rapid increase in the ion temperature, where actually at the end of the pulse, the ion temperature exceeded the electron temperature. And VPIC simulations, which are an LLE-LANL collaboration, specifically with Lin Nguyen here at LLE and Lin Yin at LANL, they capture the physics of ion heating. And I'm here showing a simpler example of a single pump interaction. And what they show is that on order 10 picosecond timescales, ions get trapped in the given wave, forming a hot tail in the distribution function. And then on order 100 picosecond timescales, ion-ion collisions re-isotropize the distribution function, although at a much higher ion temperature. And I'll just point out that predicted ion heating was broadly consistent with Manley-Rowe, meaning broadly consistent with what you would expect just from conservation of energy in the three-wave process. That goes back to my intro slide about 50 slides ago. However, I found the energetics very striking. So we heated our gas jet plasma with about 2 kilojoules of laser energy. The pumps then transferred about 16 joules to the probe beam, which meant that about 16 millijoules goes into the plasma waves, which sounds negligible, and yet that was actually sufficient, more than sufficient to explain a 10x increase in the measured ion temperature. So that just shows you that, plasma wave or plasma instabilities can have a big feedback on hydro conditions. The ion heating in the experiment both shifted the resonance frequency and increased the ion damping, both acting to reduce the energy transfer. So this is a rough calculation that just shows, this was the expected cross-beam energy transfer resonance for the initial conditions. And so Aaron put his, top 9 wavelength here in order to get the maximum expected energy transfer. But then after significant ion heating, the plasma conditions have changed, and that shifts the resonance to the right through the 3dI correction in the sound speed. And it also broadens the resonance through the larger ion lambda damping. Interestingly, though, accounting for the increased ion temperature in the high-intensity top 9 shots brings linear kinetic CVET theory back into agreement with the measured gain data. So Aaron has measured hydrogen and nitrogen independent temperatures as a function of time. And if you plug that into the linear kinetic seabed model, you actually are able to obtain agreement with the full time-dependent seabed measurements. And that suggests that the linear kinetic model remains valid, meaning there should be no need for saturation clamps. However, the hydrofeedback on plasma conditions needs to be taken into account. And this ion heating mechanism has implications for both indirect drive and direct drive. So, of course, Pierre-Michel was way ahead of the game here, and he has known about this for 10 years. So ion heating was considered for indirect drive in the early 2010s and found to be important. He calculated expected ion heating rates on the order of 4 keV per nanosecond. Aaron's results are essentially the first experimental application of those predictions. My understanding is that the default inline seabed model does include ion heating in the rad hydrocodes Livermore. So essentially, Aaron's results just validate that model. In direct drive, we're possibly behind. So their flow is more important than wavelength detuning. But there can be a redistribution in the total energy of the ions from flow energy to heat, meaning that seabed will stagnate the ablated coronal plasma. This is not currently modeled, and it remains future work, but it could significantly change the coronal plasma conditions and even seabed itself. Essentially, stagnating the flow is removing the resonance condition that underlies the crossbeam energy transfer in the first place. And so it's very analogous to the ion heating that we've seen in the stationary plasma, that the process itself can feedback on the conditions in a way that turns off the instability. And this will be assessed within the next year or two. So that actually gets me back to my summary. So I won't go through it again. I'll just say that I hope you'll see that the two themes running through the talk were both crossbeam energy transfer and non-Maxwellian distributions, and that we've made some headway on improving our understanding, particularly with respect to crossbeam energy transfer in the past few years. And I'm happy to take any questions.
Thank you very much for the very nice talk. So please enter your questions in the chat field. And also I invite everybody to unmute yourself so we can give David Turnbull a nice round of applause. I guess I'll get the ball rolling on questions. So I was curious, how do you take into account spatial variations and the distribution functions? So how are you only sensitive to like only one part of the plasma?
That's a really good question, and you know, fortunately for us with the gas jet platform, we tend not to have to worry about that. It's we've worked to refine the gas jet nozzles themselves to provide very homogeneous initial conditions. And we tend to heat it fairly isotropically so that we get a very isotropic plasma. So we usually don't have to worry about gradients so much in our plasma. These would be much more challenging effects to infer in a more complicated environment, such as an LEH, for example.
Okay, yeah, that makes more sense. Thank you. There's a question from Rich London. It says, great talk. Going back to JLF experiment, does the ion heating mentioned at the end of the talk affect the gain versus delta lambda curve? What about flow velocity?
Yeah, it's a really good point, and I would say we have not We have not really gone back and verified that the insights we have now with ion heating being clearly what is responsible for the apparent saturation at omega. We're not positive that that is necessarily applicable to the Jupiter results, but it is likely that was the case. And so the saturation clamp that we invoked was probably a red herring. It's probably likely that you can drive ion waves at the several percent level, and that they don't grade via fluid saturation pathways such as decay into other plasma waves or two ion decay, instability, things like that. We think that the plasma waves remain stable and that ion heating was likely just something that we were blind to at Jupiter. I didn't catch the second part of the question about flow velocity.
So it's just, what about flow velocity?
Yeah. It's actually a good point, because I should have maybe said that there are two effects there. So there's conservation of energy, which is maybe easier to understand for generating the ion heating, but there's also conservation of momentum. And so even in these stationary plasmas, the initially quasi-stationary plasmas, the seabed itself will generate a flow. And that's a little bit harder to identify in our experiments here, but I think Aaron would say that he is able to see that in the Thomson data, that you can see the generation of a flow. And both of them are involved in the saturation pathway.
So if there are people having trouble with entering question in the chat field, just signal me in any way, and you can ask your question. Also, I want to point out, I think it's really cool that you have both electron and ion measurements, that you're able to span those scales. Are you thinking about experiments like looking at electron-ion coupling, maybe temperature relaxation between species? And I'm sure there are many different things you can look at with all that neat data.
It is a quite rich platform. I'm certainly not thinking about that yet. It does seem like a platform that you could use for such measurements. I think there are already kind of a lot of moving parts. There are, the effects of heat transport is maybe something we've not yet dug into very much, and are starting to, in terms of how that also affects the electron distribution functions. Clearly, when we're looking at target chamber center, the center of these heated plasmas, we're maybe not, we don't have too much knowledge about what heat transport is doing elsewhere in the system, but that's something that we're digging into. Electron ion equilibrium is not something that I've yet thought about.
Okay.
Excellent presentation, David.
Thanks, Bill.
Do you have any thoughts on potential role?
Having trouble hearing.
Yeah.
The question was about the role of speckles in what you talk about. The speckled laser beam, where there's actually then a bunch of intensities in the laser beam.
Mm-hmm, mm-hmm. It's a good question, and one that remains somewhat open. So we think in general speckles don't have much of an impact on cross-beam energy transfer in most situations. Russ Follett has a paper on that for direct drive conditions. There's essentially, as long as the I think the general conclusion is that as long as the interaction length is long compared to a speckle length, then you just wind up averaging over many speckles, and you get the same crossbeam gain that you would expect if you didn't know anything about the speckles, if you were just considering the plane wave. There's some question maybe as to whether speckles impact the Langdon effect and the non-Maxwellian distribution functions. Our results would suggest that they don't. We're just using plane wave intensities, plugging those overlapped intensities into the Jean-Pierre Mott formula, and it does a quite good job of reproducing the measured super Gaussian distribution function in a lot of cases that we've seen now. In Mark Sherlock's simulations, I think he's found that that may not always be the case, and in the case of a single beam, spatial smoothing of the Langdon effect may mean that you get a super Gaussian distribution, which is slightly different from what you would expect using a plane wave intensity in the Mott formula. So there's something that we haven't quite closed the loop on understanding that. But we're certainly thinking about it.
Are there any more questions? If not, oh, here we go. Can you show slide 43 again?
Yeah,
what
I
is
would
important,
just say,
and what are the uncertainties in the data velocity where the curve flattens or turns up?
yeah, both are really good questions. I would say that of everything I've presented today, this section is the work that I was least involved in, and so I would really have to direct you to Avi Milder for that. I believe he has a paper that I think is still in review, and it should have uncertainty at each of these points, which was not on this earlier plot. So the error bar should be there, and he could speak to that more. Quartz, I couldn't really tell you other than it is Mark Sherlock's code, and he can tell you more about it. It definitely seemed to do the best in terms of explaining the tail and the distribution function, but didn't quite match the onset or of deviation from the super Gaussian nor the amplitude of the tail. So I'd encourage you to ask Mark for more about that.
So Mark's on the line if you want to pipe in, Mark.
Yeah, hi Richard. It's just a particle simulation code, so you can kind of think of it a bit like a pit code, essentially.
Okay. Well, if there are no more questions, let's thank our speaker again.
Thank you, guys. Thanks for your interest.
Yeah, thank you very much.
Thanks.
Thanks. I hope everybody has a great rest of your Thursday, and thanks for joining us.